Hello, and welcome to this presentation, Getting Started with the CMA180 VoIP Testing. In this presentation, we'll explain how to use the Voice over IP or VoIP features of the Rohde Schwarz CMA180 radio test set. This presentation provides an introduction to basic VoIP transmit and receive testing. The CMA180 also supports more advanced VoIP testing, such as transmit audio delay and voice quality evaluation using Polka. We'll only very briefly mention these advanced topics in this presentation, so please see the separate presentations, Getting Started with the CMA180 VoIP audio delay testing, and/or Getting Started with the CMA180 Polka testing, if you'd like more information about these advanced test scenarios. Let's start with a brief overview of two-way radio testing. Radio test sets have traditionally transmitted and received audio in two different ways: as RF modulated by an analog audio frequency signal, or as the electrical analog audio frequency itself. Some types of modern radios are, however, able to send and receive audio over so-called VoIP, or Voice over IP interfaces. In particular, this is becoming more common in air traffic control and military or tactical radios. In this case, the audio is digitized and encoded into IP packets for transmission. Setting up and managing these IP connections requires the exchange of control information, or signaling, which is most often in the form of Session Initiation Protocol, or SIP messages. As a result, modern radio test sets require VoIP interfaces in order to fully test these kinds of modern radios. The Rohde Schwarz CMA180 radio test set can perform VoIP testing when equipped with option CMA K610. This allows the CMA to use its integrated LAN interface to both generate or send voice over IP encoded audio to a radio under test, as well as to receive and analyze VoIP encoded audio. And as mentioned earlier, the CMA supports both basic transmit and receive style testing, as well as more advanced VoIP test scenarios. Note that the radio or device under test must be compliant with the relevant sections of various EUROK VoIP-related standards, such as ED136 and ED137, since one of the most common applications is testing of VoIP-enabled air traffic control radios. There are two basic VoIP testing scenarios. In the transmit scenario, the CMA180 generates VoIP packets and analyzes the audio demodulated from a received RF signal. In the receive scenario, the CMA180 generates an AF-modulated RF signal and then analyzes the audio in the received VoIP packets. In both scenarios, it's also possible to use an analog AF signal instead of an AF-modulated RF signal. In addition to these basic tests, the CMA180 also supports two more advanced VoIP tests. The first is measuring the delay through a network or device when the input is VoIP, and the second is measuring voice quality through a network or device where VoIP is used either as the input or as the output. In this presentation, we'll only cover the basic scenarios, so please see the separate presentations to learn more about the advanced scenarios. Let's begin by going through how to configure a transmit test. In a transmit test scenario, the CMA180 sends VoIP packets to the radio or device under test. This radio uses the audio in these received VoIP packets to modulate and transmit an RF carrier, which is received by the CMA. The CMA will then demodulate and analyze the received audio. We configure this test under the TX measurement scenario. Simply click on the global toolbar and then choose TX under the Analog tab. Once the application is started, press the folder icon to toggle between Split Mode, which shows the generator and analyzer applications side by side, and the Merged Mode, where only one application is visible at a time. The first step is configuring the generator to send VoIP packets, as well as to send messages to activate the PTT, or push-to-talk function, of the device under test. The most basic configuration parameter is the frequency ID, which must be the same as the frequency ID of the device under test. Pressing the link icon to the left will copy this frequency ID to the analyzer settings. Next, we must match the URI to the settings on the DUT. The SIP field should be set to the SIP name of the DUT, and the @ symbol should be followed by the DUT's voice over IP interface address. The AF, or audio frequency generator settings, control what kind of audio is encoded into the VoIP packets. And in this example, we've configured the audio source to be a tone at 1020 Hz. Note too that the VoIP, PTT, and AF generator checkboxes must all be individually enabled. Once these boxes have been checked, generator output is started by pressing the play button within the generator window. If the connection is successful, the generator tab LED will turn yellow. The PTT or push-to-talk LED will also turn yellow, and this indicates that the DUT is transmitting. With the example configuration shown here, the VoIP packets generated by the CMA will contain a 1020 Hz tone. The stop icon can be used to halt generator output. Additional generator output settings can be accessed using the icon in the lower right corner of the dialog. But before we discuss these additional configuration parameters, let's pause for a moment to look at frequency ID and URI information. Both of these can be accessed by their respective icons. Clicking on Frequency ID displays a pop-up showing the frequency ID and the actual transmit frequency. Note that for 25 kHz channel spacing, these will be the same, but the frequency ID and transmit frequency will, however, be different if 8.33 kHz channel spacing is used. The URI icon can be used to see VoIP connection information, including the state of the connection, for example, established or terminated, as well as any response codes, if applicable. Now let's come back to the additional generator parameters. The VoIP on checkbox is used to enable or disable VoIP without changing the state of the generator. The DUT URI is the VoIP address of the DUT, or radio under test, in the standard SIP format of SIP:user@IP address. Note that a port number must also be provided. The user part of the CMA180's URI can also be specified if needed. And PCM codec shows the codec type in use. This is an information-only display, since this is automatically set to the codec type requested by the DUT. The last group of parameters includes the PTT on checkbox. If this is enabled, a special PTT header extension is included in the VoIP packets, and this is used to cause the DUT to begin transmitting an RF signal. Recall that the frequency ID must match the frequency configured on the DUT, and this is given in ICAO channel format, that is 6 digits with a decimal point in the middle. The displayed transmit frequency and channel spacing are derived from this frequency ID. And lastly, the checkbox Apply to Measurement RF causes this frequency value to be copied to the RF measurement or analysis function. Assuming the DUT receives VoIP packets and uses them to modulate an RF carrier, the CMA can simultaneously analyze this RF carrier and the demodulated audio. In the interest of time, we won't cover these measurements in detail in this presentation, so please see the separate presentation, Getting Started with the CMA180 Transmitter Measurements, for more details. Also note that coupling the generator and receiver AF tone frequency is highly recommended, especially when not using the default value of 1000 Hz. This can be done under Analyzer Configuration, AF settings. Now let's look at the VoIP receive scenario, in which the CMA is receiving audio via voice over IP packets. Here again we have the CMA180 and the device or radio under test. For this scenario, the CMA will source an RF carrier modulated by an audio signal. Upon receiving this signal, the DUT will demodulate it and then encode that demodulated audio into VoIP packets that are sent to the CMA's LAN interface. Since the CMA is testing the information received from the DUT, this is referred to as a receive test. To configure a receive test, click again on the global toolbar and then choose RX under the Analog tab. And as before, once the application is started, press the folder icon to toggle between split mode and merged mode. In the RX scenario, the generator is configured to produce an audio-modulated RF carrier with a user-defined frequency, level, and modulation type. Depending on the selected type, the modulation parameters are also selected by the user. In this example, we're using AM, so the AM modulation depth must also be configured. In the AF portion of this dialog, the modulating audio signal is defined, and here we're using a single frequency tone at 1020 Hz. The generator is started and stopped using the Play Stop button in the upper right corner of this dialog. On the analyzer side, the CMA must be configured to receive the VoIP packets from the DUT, and this is done by clicking on the VoIP icon in the analyzer screen and by checking the VoIP checkbox. The frequency ID and URI entered here must match those on the device or radio under test. And as before, it's recommended that the transmit and receive tone frequencies be coupled together under the Analyzer Configuration dialog. The VoIP connection is established and analysis is started using the buttons on the upper right. While running, both numerical and graphical results are shown for the received RF and demodulated audio. Two additional indicators are the squelch LED and the RSSI display. The squelch LED turns yellow whenever the CMA breaks squelch, and the RSSI display shows received signal strength. This will change with the received RF level at the CMA input. Before we conclude this presentation, let's briefly discuss a few considerations when making measurements of audio carried via VoIP. Many VoIP networks use a standard sampling rate of 8 kHz, and due to the nature of analog to digital conversion, the ITU-T recommends that single-tone testing use a frequency of 1020 Hz rather than the more traditional 1000 Hz tone. The reasons for this are somewhat complicated, but audio quality measurement results will be substantially worse at 1000 Hz compared to the same measurement results at 1020 Hz. For example, here we can clearly see higher levels of distortion, both visually and numerically, for 1000 Hz compared to 1020 Hz. In addition, both the ITU and URI recommend only testing audio frequencies up to 3400 Hz. This means that for VoIP transmitter measurements, a 3.4 kHz low-pass filter should be manually configured in the demodulation path, whereas for receiver measurements, the CMA automatically inserts this filter into the input path. Please see the CMA180 documentation if you'd like more details on these special considerations and how to implement them. Let's end with a brief summary. The Rohde Schwarz CMA180 radio test set supports several types of voice over IP or VoIP testing. The CMA can send VoIP packets to a device or radio under test and receive modulated RF, and this is referred to as transmitter testing. Conversely, the CMA can also source modulated RF and receive VoIP packets, and this is called receiver testing. We covered both of these scenarios in detail in this presentation. Two additional types of VoIP-related tests are measuring the transmission delay through a VoIP-enabled radio, as well as measuring voice quality using the ITU-T Polka speech quality algorithms. These are both covered in separate presentations. For all of these scenarios, the VoIP, RF, and AF parameters are all user configurable, and audio measurement results are shown both numerically and graphically. And finally, we briefly touched on some of the special considerations with regards to single-tone testing of VoIP-enabled devices. This concludes our presentation, getting started with the CMA180 VoIP testing. If you'd like to learn more about VoIP testing, radio testing, or the CMA180 radio test set, please see the links in the video description.
Thanks for watching.
Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.